Okay, roughly speaking, okay, what is called surface patch? Surface patch must be kind of like a one-to-one homomorphism, but we only consider small surface patch. So most surface patch meets the following condition, just like similarly, like just actually just a map, okay? A smooth surface patch. Okay, a smooth surface patch is just a map into, this is an open set into R3. Okay, it is going to be homomorphism, just one-to-one, no continuity. We don't want to get very detailed. Okay, first of all, it's a homomorphism. Second, it's smooth. Okay, now so this is called a smooth surface patch. A surface in the space means you can cover it by so many small surface. For example, a set is called a surface. Okay, this is called a surface if it can be covered by many small surface patches. Okay. That means it's roughly speaking, yeah. So S is a surface means at every point you can find a neighborhood, okay, in R3, okay, so that this is W, right? It's R3, so that this is the intersection part, okay? It's going to be an image of a small surface patch, okay? So at every point there's an open domain, okay? So that this is a sigma is going to be the image of of the sigma, okay? So that is it's so if the surface is covered by those open sets, each open set is going to be an image of the smooth surface present. It's called a surface. Okay, and we actually requires another property. This must be regular. Okay, regular means the linear. Okay, those two vectors are going to be linearly independent. So we also assume that. Let me put a regular condition. A regular surface, the third condition is sigma u, sigma v. This cross product is not going to be zero. Okay. Otherwise, we have a lot of troubles in the future to dealing with the surfaces. Okay. So some surfaces, okay, in the space cannot be the image of one single homomorphic, one single regular smooth surface patch, okay? But like a surface like graphs, yes, okay? For example, if S is the graph of a function f with the two variables x and y, okay, on some domain open set in R2, then S is a surface. If this is a smooth function, then it's a smooth surface, okay, only covered by one single smooth patch. Covered by only one regular smooth surface patch. Okay, and it's easy to construct such one. Okay, so the construction we already did that before. Let me write down the sigma. Okay, this is a sigma is going to be u into R3, and sigma If you use a UV, then this is just a UV. If you use XY, you can use XY, okay? Then f of XY, f of UV, okay? And this is f is smooth, so that's why it's a smooth, and it is a one-to-one homomorphism, and more important, it's regular, okay? Because the third property must be satisfied. All right, yeah, this is a definition. Definition of the surface. I think it's given here. You see on page 77. Okay, so we always assume a surface patch is regular. Okay, it is not only just smooth, and the third condition must satisfy. Okay, it's only smooth and the homomorphism. It's a homomorphism, or just a regular surface patch. A surface patch. Sometimes for simplicity, we do not mention smooth. We just say it's regular. It's just regular surface patch means three conditions. Smooth means as a vector function, it's differentiable through. Okay. Now, if it's not, if it's just then if the set is covered by set S is covered by regular surface patches, then this is called a smooth surface. Okay. The graph of a smooth function is always a smooth surface covered by only one regular surface patch. You don't need to mention smooth. Okay. Now, today we are going to talk about smooth maps. How to define the smooth maps? How to define the smooth map? Okay. Suppose you have a map. Okay. It's from a surface to a surface. Okay. Maybe this surface is torus, and here's a sphere. It's possible, right? So I have a map, and map F. Okay. This is S1. This is S2. And both are those are smooth surface, right? Smooth surface. So this is a smooth surface. Okay. How can I say F is a smooth map? Okay. How can I say F is smooth map? Okay. How to make right? F is just defined on the surface, not on the domain in R3. Okay. But it can be explained in the following. Okay. F is smooth if F is smooth if the following condition is satisfied. How can I do that? What I'm going to do is I take an arbitrary. You see, when I say smooth some neighborhood, right? So what I'm going to do is this area I'm going to cover it by a regular surface patch. Okay, from U1 to that. Then here's the image area. I also take another surface patch. Okay, that's called sigma 2. Right. So, so this is a point P in the neighborhood of point P. Okay, and this is a Q, right? Q in the neighborhood of Q. I have another patch. Then what do you get? Then you get a map. Okay. Then you get the map actually from U2 to U3. It's a two variable function, vector variable function. So I can get this map. How can I describe this map? Well, you go this way, right? Sigma 1, then compose it with F. Then you have to pull back the inverse. So this one is a map from here, from U1 to U2, okay? So this map, because this is a two open setting in R2. So you can view that as a vector variable function has two components. So if this is a smooth, means it's differentiable many times, okay? That's the That's a reasonable definition. And you can also check this will be independent of the, it will be independent of the choice of this regular patches you're using. I just say for some. Okay? If there exists, if there exists sigma 1, U1 to S1, and sigma 2, U2 to S2, such that, okay, this map from U1 to U2 is smooth. Okay? And because we can only talk about smoothness of a vector value function, define an open set, not on the surface. So that's why we have to convert everything to a map from to a vector value function. Okay, maybe multivariables, right? So this is the idea. So the picture is quite clear. It's not the the picture is not it's quite clear. Okay, then so we already have a we know how to say a function smooth, right? A map is smooth. Now, the important factor which I don't want to check is the smoothness independent choice of sigma 1, sigma 2. Here's the important fact. Okay? The smoothness of F is independent of the choice of particular regular surface patch. Okay, surface patch sigma I from UI to SI. I is from 1, I is 1 or 2. Okay, so you can choose another one, still the same property holds. Suppose for some regular patches, sigma 1, sigma 2, so that this function is smooth, then you choose another regular surface patch, you will end up with the same result. The reason is because between two regular surface patches, the Jacobian will be smooth. Okay, as a combination of the function will be smooth. The main reason is that, okay, I just want to give you the idea as to why this is true. So if you have this is a point P, right? Suppose there's two sets, right? This is a sigma 1, U1, and here another one, sigma 2, sigma 1 tilde, right? And then you have a map from U1 to U2 and back, right? So this capital is going to be, right? Or its inverse. Okay, so this is from U1 to U2, that's from U2 to U1. So we know that those two are they are smooth. Right, those two must be smooth. Okay, they must be smooth. So doesn't matter which one you're going to use. Okay, the smoothness will not change. Okay, and I can say suppose you sigma 1 replaced by sigma 2. Okay, suppose sigma 1 replaced by 2. Let's look at the function, above function, right? So above function, yeah. See, look at this, right? Okay, suppose I change it to sigma 1. Okay, tilde, another one. So why this smoothness will not change, right? So you can write in the following one. Okay, so according to our notation, this is a sigma. Yeah, minus. Yeah, it's not. There's no minus. Yeah. Right. So this is just as the inverse function, right? Okay. So and we know that this is a smooth. and this is also smooth, right? So that's why the composite of these two maps will be smooth. Okay, that's why it's guaranteed. Okay, so this is just because those two just this function is smooth. This map is smooth map. Okay, okay. So that means if it's smooth, then this is a smooth. Okay, double picture. So that's why another student use another regular surface patch to check the map F, right? The smoothness of map F, and he concludes that it's smooth. Then everybody else in the class, right, use their own favorite regular surface patch to check the function. This also should be the corresponding, the resulting function map should be also smooth. It doesn't matter which regular patches you choose. This is the idea. Okay, and so let's try to take a look. Let's look at some examples. I'm going to find the map. This is a special surface, S1. This is in R3. Okay, this is actually consists of X, Y, and so the component Z, right? Or I can use doesn't matter, right? X and Y. Okay, there's no restriction on X. Okay, this is just a flat. This is XY plane, right? This is typical surface in R3. Then I look at the consider cylinder. This is another surface in R3, right? So the cylinder, how can I describe cylinder? X, Y, Z, and X squared plus Y squared equals 1, right? No restriction on Z. So this is another surface. Okay. So both are surfaces. Okay. We already, I think I already proved that. Both are S1 and S2 are smooth surfaces, okay, in R3. Okay. I'm going to construct the map. Okay. I'm going to construct the map F. Then I want to check whether this is a smooth map. So how can I do that? I just fold it, right? So I'm going to, I'm going to define the value of the point to be, okay, it doesn't matter, right? So it's going to be cosine X, right? Cosine Y, sine X. And then the third component is what? For example, okay, what I was trying to do is I folded this piece of paper to make a cylinder. Okay, so it's clear that this is this is in S2, right? This is So it's clear that F is smooth. How do you see that? F is smooth. And this map F actually can be viewed as a regular patch of this actually is a regular patch of the cylinder. Okay, so let's see. I'm going to consider sigma 1, right? This is from R2 to R3, okay, and that will be UV, 2, UV, and 0, right? Okay, that's the standard one. And the sigma 2, okay, and again, the way R2 to R3, and this time, I'm going to use UV or S. What kind of variable I'm going to use? I want to use different notations. It's okay, it doesn't matter, right? So use the same variable is fine, but that's for the cylinder. Right. It's going to be cosine U, sine V, and sine U and V. So what do you get? Okay. So this is a plane, okay? So this is sigma 1. And here's the cylinder, right? Sigma 2. Now, here I have to put a restriction, okay? I cannot have the sigma 2 is not going to be one-to-one. It's not going to be homomorphism. So this time U is going to be between 0 and 2 pi. That's only restriction. Okay. Actually, we only have a trip. This is a U and the V is 2 pi. Yeah, this whole piece, okay, forward. Okay, here, this is a whole plane. Okay, it's the same. Okay. This is just a half. All right, so now, then you can talk about the inverse, right? Then the map, right? So UV, let's see, what is that? Right, it's going to be just UV0, right? And according to our definition, it's a cosine U, sine U, and the V, okay? And that, from our definition of this, right? So clearly this is just equal to U and the V. Okay, so actually this is identity map. Okay, send the UV to UV. Okay. Of course it's a smooth. Is an identity map. Okay, so clearly it's a smooth. Okay, okay, it is smooth. Okay, it is smooth. So therefore, we almost prove F is smooth, but you know, a sigma 2 does not cover the whole cylinder. I have to say that it does not cover this line, this vertical line. Okay, it's not covered. So you know, if well, by similar argument, you choose another sigma 2, okay, and then cover this whole line. Then with that sigma 2, you will get another function, another map, which is clearly it's also smooth. Okay. Okay. So in order to prove smoothness, this is not the complete proof yet, and you have to define another one to cover the vertical lines when yeah, you have to cover this vertical line in 3-dimensional space. The z-axis, right? Not z-axis, the line. This is a good point. Center. So this is 1, 0, 0. Okay. So you have to cover this line. To, yeah, we choose another one. So it is a smooth, but that this not complete. This is not complete proof. You have to find the sigma prime, for example, right? sigma prime or sigma 2, yeah, it's okay. So that is going to be U2 to R3. How can I cover this, right? It's not U2, which is going to be, yeah, I still use a U and the sine U and the sine V, but this time instead of from 0, I can do it from yeah, from pi to, right, pi to 2 pi and to 2 pi, so 3 pi. Okay. How about like that? So this is still, yeah, this is a still, this is a U2. Yeah, this is a map. Yeah, actually it's from this thing, right? From this. Right, so this is my my map. Okay, this is a regular patch for the cylinder. Okay. Now we have to be very careful. Okay, we have to be very careful. Sigma, okay, F is going to be cosine U, sine U, and the V. So this is a, yeah, this will be a little bit, okay. Yeah, it's the same. I think just our sigma 1, okay, sigma 1, yeah, the same actually is UV, okay? Now be careful about this. And in the second case, sigma 1 is also should be the same set from R2, but you don't need a, see, you don't need all the variables, okay? So this is also going to be the U1, but U1 this time, yeah, we have to choose a different, yeah, because yeah, it's the same, you know, it's a sigma 1, 2, not instead here, okay? So this is a from R2, but yeah, this is from, let's see, I'm going to say U and the V is between pi and 3 pi, okay, into R3, okay? So sigma 1 to the UV is going to just UV and the 0, okay? And there's the same here, there's a restriction. So this is my U2 tutor, okay? This is U1 tutor, okay? Even the above picture here, it's not true on all UV here. Actually, UV, U is already has a restriction from between 0 and 2 pi. As the reason is you only consider, yeah, you only consider this portion as that's U1 from 0 to 2 pi. The reason is all you need is this piece, okay? Otherwise, there will be a little bit trouble here, and to find, you know, the value, if the value of the U is too large, then I have to modify it. I'm not going to get identity map, okay? I'm not going to get identity. Okay. Yeah, if there's no restriction on the U, then if suppose the U is greater than 2 pi, right? Then I have to modify this. So this map will send UV to another map maybe here minus 2 pi, something like u minus 2 pi. So it's not necessarily the identity map. Okay. So it depends on what domain you use for the U1. Okay. For the U1, you still have to assume that 2 pi. Okay. Then then you get identity map. And similarly, if U1 tilde and U2 tilde is determined by this inequality, then you still have this identity map. Okay, so then of course it's a smooth. Okay. So for every point, on the wait a minute, yeah. So for the function f is defined on the whole plane. What we did here, okay, we showed that the function is smooth. Okay, we showed that the function is smooth on the interval from 0 to 3 pi. Okay. So this only showed that. Okay, this only showed that because the map F, that's a good question. You see, the map F is from R2 to a cylinder, right? Okay. So we only showed that the F is a smooth from 0 to 3 pi. Okay, right? And how about the other area? Other area is repeated. It's a periodic function. So you can always the only difference here, if you choose for example for UV in R2 was U is greater than 2 pi and less than 4 pi, right? In that case, okay, and your sigma have to start from here, right? It's defined, right? Then the only difference here is, I think, let me give you one example. So I'm going to cover that domain, okay? So let me U1, U is between pi, 2 pi, and 3 pi, suppose, right? Okay, so sigma 1, U1, 2 3. Right. So that is still UV 0, okay? And I'm going to still use sigma 2. Right. So sigma 2 and UV still use 0, less than U, less than 2 pi. Right. And sigma 2 okay. Right. This is a So this is a so now, okay, F sigma 1. So this will be U1 to U2. Okay, how can I find this map? Okay, be careful. And then you will have cosine U and sine U and V. So be careful about this. Now, sigma 2 is from here to the cylinder. But this UV, this U is actually outside the domain from 0 to 2 pi. So what you have to do is you have to change it to minus 2 pi, right? Sine U minus 2 pi and V. Then this is a U minus 2 pi V, right? So that's only small difference. It's not a really identity map, but you may send the UV to U minus 2 pi and V. Okay, so in that case, it's a still smooth, right? Okay. So anyway, what I want to say that F is smooth, on the whole attitude. Okay. You have to prove that smooth at every point. So you find a regular surface patch for S1, and then you consider this combination. Yeah, it's a little bit. It's a little bit. Yeah, it's a little bit complicated here. Okay, now we can. Let's try to look at. Yeah, let me talk about the diffeomorphism. Okay, so if F is from S1 to S2, okay, this is called a diffeomorphism if it is homomorphism. Now, what do you mean homomorphism, right? Homomorphism means and F and its inverse are smooth. Right? Now, homomorphism means two things. It is 1 to 1 and on 2. Okay? Second, it is the map itself, but this condition is not necessary. We already have the next one. The map, those two mappers are smooth, are continuous. Okay? So the key point is 1 to 1 on 2. So you can talk about the inverse map, right? The inverse map. Then they both should be smooth. And our above function F is not a diffeomorphism. The reason F is not on 2. So above map, this is not on 2. Right? Yeah, the above map is not on 2. So it is not a diffeomorphism. Right? It's not a 1 to 1. Yeah, it's not a 1 to 1, but it can be on 2. It's just overlap, over somewhere. Okay, I'm going to look at the next problem. Yeah. So I want to talk about attaining the vectors. Okay, suppose you have a surface. This is S. Okay, define an abstract way. It's a smooth surface, means it is covered by regular patches. Okay, maybe not unique, okay? It's not covered by single surface patch, otherwise topological trigger. So like a sphere, like a torus, you cannot find a single, so you have to find different. Right, so I want to define the tangent plane, how to describe the tangent plane. In the space, yeah, well, how do you know that's tangent plane? You have to define the tangent vector. Okay. So this is point P. Okay, how do you define the tangent vector? Okay. A definition here. V is called attaining the vector. Okay. To the surface S at the point P if it is a tangent vector to the curve, right, on the surface, right, passing through P. So namely, V is going to be gamma prime 0, right, where gamma is from, let's say, we just assume that from a small neighborhood to the surface, okay? And such that this is going to be the point P. Okay, how do you describe it? All right, so this is a curve, it's gamma, right? And this is a map, gamma. Okay, that's the point P. Okay. So we know how to find the tangent vector of the curve, just differentiate. Right? So let's describe all the tangent vectors to see what kind of effect we're going to get. Okay. So what I'm going to do is, this is surface again. I have to draw lots of pictures, okay? So I have a regular surface patch. And this is a point P, and here, right? So this is sigma, right? So for any A and B, right, which are not going to be 0, 0, right? I can let VT be a curve in R2. Right? Be a parameterized curve in R2, right? Such that they're passing through this point. Right? And this is tangent vector. Right? And U prime 0 equals A, U prime 0 equals B. We can do that always, right? Then gamma T sigma UT VT is a curve on the surface, right? Yeah, such that Okay, passing through the point P. But the gamma is a map from R to the space. Okay, this is a map, right? It's gamma. All right. So now let's take a look at the look at the attaining. This is attaining the vector, right? To the curve, by definition, it's attaining the vector to the surface. So when I differentiate, I use a partial derivative, right? I get this plus. Okay, so it's linear combination. It is linear combination. Okay. And A, B are arbitrary number. So we conclude as a set of all tangent vectors to the surface at the point P, okay, is denoted by TPS, okay? And this is actually is spanned by those two vectors, okay, because AB arbitrary. Okay, so we conclude that we see that this set is going to be a linear combination. And A, B are arbitrary real number, okay? So sometimes we just simply return two, yeah, it's spanned by these two vectors. Right. All right, so this is how do we describe tangent space? Tangent space, yeah, this is called tangent space. And this is a two-dimensional space, right? The dimension, yeah, TPS is a vector space. And since this is the place where we require the regularity of the sigma, right? And the dimension, this is 2, and since sigma u, sigma v are linearly independent. Right, that's a linearly independent. All right, so let's go back to the picture again. Okay, I'm going to show you the picture again. Understand, this is a point. And this is point P. So this line, this horizontal line being colored, okay, I use the red color. So this will be here like that. Okay, it's curved. And then let's get another. Then this one, going this way. It's here. Okay. So this tangent, this is a tangent vector, sigma v. Right. Right, that's a picture. Okay. So those sigma u and v, sigma v are both attaining the vectors because to the tangent to the point. Okay, and the geometric meaning of each vector is actually the tangent to the to the curve, okay, coming from this horizontal line and this vertical line. Okay, so sigma u is tangent to the curve. I call it U curve maybe. Okay, gamma u, and so it's a u is 0. Okay, u to 0. Okay. Well, it's not good impression. Maybe I just call it gamma 1. Okay, and yeah, this is a curve. If you fix the v, then you get a curve. And the different horizontal line, you get different curves, right? Right, let me describe tangent vectors to some surface. Right. So describe the surface patching. Right. U minus V, U plus V, U squared plus V squared. Okay, it's how to describe the surface. No restriction of the U. V. So sigma is from R2 to R3, and its image. I think it's a 1-to-1. Okay, this is a yeah. It does not have a self intersection point. So let's describe. So it's harder to draw the picture here now. Okay. So this is a surface here, and this is the map from R2 here, right? U and the V. Next, the center point is sent to here. Right? You can use X, Y, Z. All right, what I'm going to do. First of all, I want to make sure this is indeed the image. You see, we have one single, right? So it's just a single map, okay? So I should say the image of sigma is a surface. It's a small surface. It's a small surface. As it's sigma. Right. All you have to do is just make sure sigma, because S is only covered by one sigma. All you have to do is make sure sigma is a smooth, sigma is a regular, sigma is 1-to-1, right? Sigma is It's a homomorphism. All I have to do is should that's 1 to 1. Okay. Second, sigma is C infinity smooth, right? Smooth for C infinity equation. This is obvious. Third, sigma u, sigma me are linearly independent. Right? And there's no other surface patches here, regular surface patch, smooth surface patch here. We just have one. Right? There's no other regular surface patches given. So it's okay. One single map can define the surface. Topologically, maybe it's still trivial. It's R2. Okay? It's not like a sphere torus. How do you check it's 1 to 1? Well, different values, okay? I want to see what we can get, X, Y, Z, okay? Can I uniquely determine U and V? If we can uniquely determine UV for some X, Y, Z, that means it's 1 to 1, because if it's different, right? Now you should have two different sets of solutions. So let's try to solve this first, okay? Just solve this equation. So here what do we get? By definition of sigma, UV, U minus V equals X, U plus V equals Y. And U squared plus V squared should equal to 0. Okay, so Z actually is not, Z is related to UV, right? So add them together, U equals X plus Y divided by 2. V equals 1 minus X divided by 2, okay? So there's only one unique point. Have the same image, have the image. So it's 1 to 1. Different points, if they have the same image, for different points, if they have the same image, you should end up with the same U and V. So that's why unique. Okay, so it's sigma is 1 to 1. Okay, but not all the points you can have an image here, right? So this is in the space. Okay, so clearly Z is going to be U squared plus V squared. So that's going to be, that's 4, right? Add them together. U squared is going to be, 2x squared plus 2y squared. So it's going to be half of x squared plus y squared. U squared plus v squared is going to be 2x squared, 2y squared, but divided by 4. So these not arbitrary. These are it's kind of parabola. Okay. This is going to be x squared plus y squared. So if you choose another point here, there's no solution for UV. So the point must be on the surface, okay? Then you can have it. So there, this is my map. Okay. So different points here, we send it to the different points. Right, so it's 1 to 1. Okay, let's take a look at sigma u. Sigma u is the map itself is u minus v, u plus v, right? And u squared happens. So the 1, 1 is 2u. Sigma v is negative 1, 1, and 2v. Now these two are linearly independent, clearly. Clearly they're linearly independent, okay? So it's linearly independent, therefore, sigma is a regular surface patch. Okay, so its image itself is just, its the image itself is a surface patch. Is a surface. All right, so you can describe the tangent space at the point sigma uv is given by right. It's going to be spanned by this two set, right? Right. Right, in the last few minutes, I'm going to talk about differential. So, you know, it's a, you can, the map actually has a smooth map, okay? Let F be a smooth map, be smooth, okay? Then point P here, and then have a point Q, Q is F of P, all right? We can define the derivative in the following way. Okay, we define dpf actually has become a linear map. Okay, as follows. How can I define? This has actually become a linear map. Okay, from S to S. So actually, this is a picture again. Here's a point TPS. This is Q, TQS2, QTS1. So this is going to be a linear map from tangent space to tangent space. How can I define? The definition is very simple. How do we describe tangent vector? We describe tangent vector in the following. Okay. We just use an arbitrary curve. Okay. Use an arbitrary curve T0 equals, right? So I have a vector. Okay, so this is a tangent vector, right? So here, how do we do that? It's going to be attaining, yeah, this gamma t is going to be sigma 1 okay. So attaining the vector in S1, right, is going to be A plus B. Right? So it's a linear combination of these two vectors. So now you have a curve here, right? Remember the picture, we have a curve here, then you have a curve here. But this curve will be sent to another curve here. So that curve, this is going to be gamma, right? And that curve I call the gamma 2. And this is actually going to be F circle gamma. So the definition dpf, it's sent, here's the definition, okay? The definition is very simple. It's just equal to gamma 2 the upon 0. So that's the definition, okay? And yeah, then if we want to get a formula, how can I do that? Compute the formula, right? So look at it, Q. All right, so this is a map into the surface, okay? Now let's differentiate. And when you differentiate, this is differentiable. Okay, then you get A sigma V. Okay. So this is a linear combination of these two. Okay. So this linear map send this one to this map, to this vector. Okay, and as long as you know the base, the image of the basis, right? Okay. So you completely determine the linear map. Okay, so I'm stopped here. Okay, so we continue to discuss the maps. How do we define the maps between two surfaces, and the induced linear map between two tangent space?